Hello, I'm Charlie Whitfield, an engineer here at Rhythm Engineering, and today I'm going to show you exactly how InSync works in a simple, straightforward way. This introduction to InSync's patented process will illustrate 5 ways InSync transcends today's current signal timing practices, adapting in real time, rather than responding to changes in traffic patterns every few minutes. InSync optimizes traffic flow by the process called intelligent actuation, evaluating real-time demand globally through a network of intersections and locally at each individual intersection in the following ways. Green tunnels and their durations. We will learn how InSync adapts in real time for fluctuating coordinated traffic volumes at each intersection to allow for optional bidirectional progression across an entire network. Adaptive periods. Different from cycles, we will also learn how InSync's adaptive periods of time are not constrained by cyclical patterns of service, thereby providing true bidirectional progression capabilities throughout a network of intersections. Dynamic phasing. Dynamic phasing is the way InSync determines the importance of service at each approach. Green time allocation. Much like dynamic phasing, I will more specifically cover how InSync uses green time allocation to equitably serve and distribute the intersection's green time to each phase while balancing progression. Dynamic sequencing. Here, we will see how dynamic sequencing comes full circle by explaining the way InSync selects from the traffic professional's allowable sequencing parameter and distributes green time accordingly. InSync's global optimizer ensures cars driving through an InSync network of intersections experiences as few stops as possible by creating coordinated green tunnels. At each intersection in between green tunnels, InSync turns its attention to efficiently serve all secondary movements by attending to the local optimizer. InSync adapts to traffic on a global level by optimizing green tunnel durations and adaptive periods. Green tunnel durations are a referenced amount of green time at each intersection. These durations are set by the traffic professional based on known traffic characteristics for the respective time of day. When tunnel volumes fluctuate outside the reference parameter, InSync offers adaptive flexibility. If the traffic volume decreases and reaches a minimum number of cars, InSync can truncate the duration of the green tunnel. InSync may also release the individual movement early before the oncoming green tunnel when appropriate. If the traffic volume increases, InSync can do a quick calculation and know if it has enough time to extend the green tunnel as well as serve all occupied secondary movements. Tunnel duration adjustments happen individually at each intersection within InSync's defined period of time. Adaptive periods. Rhythm Engineering coined the term period for traffic operations to describe the time it takes to serve the green tunnel as well as dynamically serve all side street approaches at least once before the tunnel is served again, rather than only in a fixed cyclical order. In traditional responsive signal timing, each intersection serves its traffic in fixed sequences, which drive the intersection's ability to bidirectionally coordinate traffic. InSync does not use cyclic operations, which limit bidirectional progression in a network of irregularly spaced intersections. Traditionally, motors on the main line may be forced to stop due to the signal timing relationship associated with irregular spacing, causing a cross street or a left-hand turn to be served instead of maintaining bidirectional progression. InSync's period length allows bidirectional progression, and it is the same for each intersection across the network in both directions. However, the period does not have limitations like traditional fixed sequencing relationships between neighboring intersections. Traffic professionals now have the ability to enable efficient bidirectional progression by removing fixed sequencing constraints associated with irregularly spaced intersections. This is done by defining how and when they want progression to occur, and simply allowing InSync to serve each intersection independently when progression is not occurring at each location in the network. If configured to allow dynamic period lengths, InSync can alter the amount of green time given between green tunnels, within a certain range set by the traffic professional, producing more time or less time for side streets and left-hand turns. For example, here, InSync sees a pattern where secondary movements, like the southbound lefts, are unable to clear before the start of the next green tunnel. InSync makes a global decision to dynamically expand the size of the period by allotting more green time to serve all movements. In this case, the period has been expanded to 103 seconds. Now watch as InSync is able to satisfy all secondary movements. In the same way, if InSync sees that the most critical intersection has extra time left over after serving all the side street demand, InSync will shorten the period by reducing the time given to all the movements. Building on these global concepts, each intersection's adaptive features are used to improve efficiency at the local level. This is done through dynamic phasing, green time allocation, and dynamic sequencing, and these are all used simultaneously with global optimization, but occur locally at each individual intersection. InSync does this by measuring Q and delay for each approach. As we see cars pull up, imagine InSync assigning them tokens for their presence and wait time. As more tokens are given out, demand increases. InSync tries to minimize the number of tokens given, attempting to serve the queue with the highest demand within the intersection's adaptive parameters. Since InSync is unconstrained by cycles, the system determines priority and serves approaches from highest to lowest demand. InSync will serve all movements, where demand exists, before the arrival of the coordinated green tunnel. Each approach at an intersection is called a phase. Dynamic phasing. Phasing is the way InSync identifies and selects which phase to serve based on volume and delay. For example, this intersection has 8 phases: north and southbound through, left-hand turns, and east and westbound throughs. InSync uses a digital state machine rather than a fixed timing plan and is unconstrained by cycles, allowing the system to choose the phases that best serve actual traffic demand within the sequencing parameters, which we'll talk about later. To illustrate demand, let's bring a few cars on the scene. As the cars show up, you will also see their demand grow in the respective demand bars above. InSync looks at the volume and the individual movement's delay in each intersection and calculates the most efficient way to serve the most cars before the tunnel is served again. The east and westbound lefts show the highest demand and serves them first. As soon as the east and westbound lefts clear, InSync now sees the northbound through and northbound left have the highest demand and serves them. The north left finishes, but InSync sees that the north through just needs a few more seconds so the cars can pass safely through. So, InSync gives green time to the southbound through while continuing the northbound through. As soon as the northbound through finishes, InSync serves the southbound left phase. As the southbound through phase clears, InSync calculates the demand of the northbound left and sees that it has enough time to reserve that phase before the tunnel is served again. InSync knows it can achieve this because it continuously evaluates how much time is remaining before the next tunnel in order to determine how it will allocate the available green time. Green time allocation. Remember that a true period is the tunnel time plus the non-tunnel time without the need for fixed sequencing. InSync must be able to serve all movements within its period. However, InSync will not waste green time by serving phases without demand unless desired by the traffic professional, or serving excess amounts of green time to phases with minimal demand. InSync optimizes passage time by doing this. Green time allocation is the process of administering the appropriate amount of green time to each occupied phase, while allowing InSync to skip empty phases as well as serve a phase multiple times within the same period when allowed. As soon as the tunnel is through, InSync knows that it must be able to serve all phases at least once before the tunnel is served again. If some of the phases are empty, like the east and westbound lefts, InSync will reallocate the green time normally needed at that phase to another phase with a higher demand, or to the reservice of a particular phase if needed. Let's watch as InSync begins to serve the demand at this intersection. InSync turns its attention to the side street approaches and serves the best 2 non-conflicting phase pairs. In this case, it's the north and southbound throughs, followed by the north and southbound lefts. At this point, all of the originally occupied phases have been served, and InSync still has extra time for another phase pair to be served before the arrival of the green tunnel, so it reserves the southbound through. These phases are organized into non-conflicting phase pairs, which we call states. States are organized into sequences. Dynamic sequencing is the method InSync uses to determine how to serve each intersection. Inside the InSync software, the traffic professional can choose allowable sequences. For example, if the traffic professional chooses not to have lagging lefts, all lagging lefts would be removed, leaving behind only the allowable sequences. InSync draws from the available sequences dynamically, serving both sides of the barrier without violating the traffic professional's safety considerations. This provides the best possible use of green time for vehicles waiting at or approaching the intersection. As soon as the green tunnel is through, InSync turns its attention to the local optimizer and serves the sequence with the highest demand. In this example, it's the middle sequence here. You can see that InSync is serving the north and southbound lefts. Notice that each allowable north-south sequence begins with the north-south lefts. InSync uses real-time information, evaluating demand before committing to a particular sequence. For example, if this state here were to somehow grow in demand, InSync would then serve that state next because it does not violate the sequencing parameter. Also note, while InSync is serving the north-south lefts, the cars in the southbound through will be making right-hand turns, thereby eliminating the demand for service. As the southbound left clears, InSync moves to the next state in the sequence and serves the northbound through, while at the same time continuing the northbound left. As the northbound through and left finish, InSync instantly evaluates and skips the north and southbound throughs because there is no longer a need for service, and simultaneously chooses the best sequence in the east-westbound direction. When choosing a sequence, InSync evaluates demand as well as the arrival of the green tunnel. InSync sees that a vehicle is waiting in the westbound through and will try to release the through movement with enough time for it to pick up speed so as to not slow down the cars in the approaching green tunnel. The westbound tunnel has been served, but the eastbound tunnel is still coming. InSync knows that it has enough time to reserve a state within that period before the arrival of the eastbound tunnel. InSync chooses to reserve the north-south lefts and the extra time based on demand. InSync crosses the barrier, serves the demand, and arrives back to serve the eastbound green tunnel. The 5 components explained in this introduction demonstrate how InSync achieves its patented intelligent actuation process. Thank you very much for taking the time to learn about InSync's adaptive process. Please feel free to learn more at our website at rhythmtraffic.com.